So, good morning, everyone. Today it is lecture number 2, and we will discuss about basic concept of probability. So, coming to outline of today's lecture, these basic concept. It may look simple to you, but my suggestion is that try to understand these things in a very deeper way. Don't leave any of the concept. Just try to don't. And one more thing to understand mathematics in a better way, what I used to apply. So forget about what you know about this. Just always start from zero, and whatever things come to you, try to understand. And if you are understanding during interaction, definitely things would be very interesting. And later, whenever that kind of concept will come, definitely you will get a maximum application of that. So that's way, just forget about history. Whatever things are going here, try to focus on that and try to learn. And if you are facing any problem, let me know. Definitely I will try to make you understand in a better way. So coming to outline of today's lecture, so I have taken two outline. One is basic concept of probability. There I will talk about that algorithmic or systematic approach of dealing with the quantification of probability or measure of randomness or a study of randomness. That systematic approach, even in your high school, you might have already seen that systematic approach. It says that you are having a random phenomena. In that random phenomena, what you do, one assumption you are putting, that you are able to visualize all possible outcome. Then that means you are having information about all possible outcomes. So what are the possible outcome would be there associated with that random phenomena, random experiment, in order to quantify the randomness. So when you take together all the possible outcomes, that collection we are calling it sample space. So once we are having a sample space, simply you in one line you can say that sample space is what it is, talking about all possible outcome. Here the word all is very important. You have to focus on all possible outcome, then that would be a sample space. Now further, if you go in, you change the word all to some possible outcome, then that statement, it will be what, it would be event. So event, how you define it, you are just saying that some possible outcome. It is not covering everything, it is covering just at at moment, whatever things are coming to you, some possible outcome. So that one is event. That one is totally subjective nature. Whoever is going to attack that kind of outcome, it would fall in that kind of event. So that's way, all possible outcome is one important ingredient of this basic concept of probability. Or simply you can say that we are trying to do some probabilistic kind of modeling. So we have already started probabilistic modeling. So it is one approach of probabilistic modeling. So there, what is the first important ingredient of probabilistic modeling? It is saying that we are having a what random experiment or random phenomena. Okay, there we are introducing first ingredient as sample space, that say that all possible outcome. Afterward, we try to focus on, we try to be more specific. Then we are saying that some possible outcome, then some possible outcome that leads to what, event. And further we will go, we try to measure the probability with respect to that outcome. And then there I will give a very simple kind of quantification as what one hierarchical approach, that it says that as a ratio number of outcome, that in which event is happening, the number of fashion or number of way the event, one event which is already mentioned there is happening, divided by total number of all possible outcome. So that hierarchical approach, it looks fascinating, but if you put some assumption over that, then it becomes very concrete kind of definition. Okay, in a very a small problem, this definition, there is no issue with definition, but later you will go to find application of this one, you will face a problem. Suppose just I'm just for basic purpose, I'm asking one question, that everyone might be aware of that tossing before any kind of game, generally, that when two team are playing, like if suppose cricket, you are watching cricket, then and just focus on Kohli. Virat Kohli, right now he is current captain of Indian cricket team. So if you observe that most of time he is unable to win the toss. So due to that, he depends upon other opposite captain. So why such? So based on that, suppose Virat Kohli, he will toss a coin, and in place of head he will get tail. Then what will happen? Several times, then out of 10 toss he got 3 times head in place of tail. He asked for tail, but in place of tail he got head only, 3 times head. So what can he say that that coin is not a fair coin, it is a bias coin? Can he claim or not? What would be probability of getting tail there? Just anyone respond. Just suppose that during that toss process, that Virat Kohli got 3 times tail in the 10 toss, 3 times tail. What is meaning? Or simply you can say that in 10 consecutive matches he got 3 times tail in place of head. You know what would be scenario? What would be scenario of that coin? Anyone can comment that? No, very wrong answer. That's based on you. Really, you answer. Your answer is right up to that hierarchical definition. It says that ratio of number of number of way the event is occurring divided by number of total possible outcome. So based on that, you answer it. But from that, your approach is fine. But if you go in long run, then you are wrong in long run. So if you try to see the truthness of this definition, hierarchical definition, that ratio it is talking about, in long run, that one is true. At that long run, we are calling it law of large number, that we will discuss in module 3. That we will discuss in module 3. Okay. So that long run, that may be true, but if you in a smaller scale, it may be false. That's why we need to put some kind of assumption, various assumptions we need to put in order to make things accurate. So that's why Kolmogro is coming here. His statement is very fruitful in order to understand probability. Okay. Any further comment? Yeah. Nice. Yeah, right. Then I'm happy that you came to know soon. Actually, I think few people can comment over that after going to module 3. So just in here in probability, always be fresh. Try to answer from honesty, with honesty. Whatever you know, just try to answer from there. So it is the best way of learning probability. Now, then second part, I will in this lecture I will talk about probability measure, how to measure, and the law of probability. Further, how many assumption we are putting there in order to quantify randomness. So that things we will discuss in detail. Okay. So coming to basic concept of probability. So first I will talk about sample space and event and random phenomena. We will start with random phenomena and then we will include sample space. So coming to concept sample space, what we do, a random experiment is an experiment whose outcome we can't predict before the experiment is performed. So before experiment is going to happen, before that we can't predict what would come. Okay, so we do however know in advance that what are the possible outcome. So that assumption, you may see here the second sentence, it is very powerful sentence, that it says that when you are performing a random experiment, you must be aware that what are the possibilities, but you are not aware of that what would come. You are not so there are two statements. One statement, it says that you know that what are the possibilities among the various possibility in that occurrence of random experiment. You know that what are the possibility, that things you are having, that we are calling it exhaustiveness property. If you try to later, I will say explain that. But you don't know that what would come. You don't know. You are not a god, so you can't predict what would come. So simply you are a human being. So from that perspective, you can't predict what will come in the random experiment. So that scenario is there in the random experiment. Okay. So if you are having such situation, for example, if you flip a coin, you know it will come up either head or tail. You just do not know which of these outcome will occur in the given experiment. You don't know. You know that if you toss a coin, you flip a coin, either head will come or tail will come. But before experiment, you can't say with 100% or with 100% same thing. You can't predict that head will come or you can't predict that tail will come. You can predict with some uncertainty. Then when uncertainty is coming, that means it is a probabilistic phenomena, so or random phenomena. So that's way. So that is the situation. So the first ingredient of any probabilistic model is the specification of all possible outcome of a random experiment. So that's why I told that in short, this property we are calling it exhaustiveness of a random experiment. That means we know about all possible outcome of a random experiment, but we don't know which outcome will come in the coming experiment. We don't know about that, but we know that all possible outcome. And the collection of all possible outcome, we are calling it sample space. Sample space, I will be very specific to notation. So most of time I will take sample space notation omega, capital this omega, capital omega. It is the notation of sample space. It is calling it is the collection of all possible outcome of a random experiment. So if you toss a coin, what are the possible outcome? Head and tail. So there are two elements in case of flipping a coin. So that is the scenario. I have taken many examples. So coming to example of random experiment and further exhaustiveness, that means recalling that what would be sample space. So suppose we are taking two dice game. So consider the random experiment of throwing one red dice and one blue dice, and we denote each outcome by order pair ij, where I is the outcome that come in the red die and j is the outcome that appears in the blue die. Okay, so it is order pair. Order is very much essential here, or that's why bracket always represent order pair. Okay, so from if you toss two dice, one is having color red, another one is blue, and if you try to collect all the outcome, then how many possible outcome you will observe? 30. Yeah, very nice. So here uh, the each out. So each point of the sample space, we are calling it sample point. So here sample point, it is notation would be bracket here. Okay, so you can trace out all the possible outcome. What would be the first outcome? Would be, don't call it first, I don't know which would be first or second. Why? You know, the not a sample space, it is talking about set is not having any order property. Anyone come first, anyone come last. So that's where order, I'm not saying order, simply I'm saying that this one is one element, one, then for simplicity we can say that it is first element, because one is always coming first. There is a well ordering property associated with a set of natural number. That's way. Then we can say that 1 2. Likewise 36 sample point or some element would be there in the sample space, and last you can say that I'm abusing some notation, so just you can relax those. There is no issue. So last I am saying that, but here sample space is a set, so anything come anywhere. So in total, simply you say that there are 36 elements in this sample space. That means there are 36 possible outcome in this random experiment. What is the random experiment? Throwing two dice together. So in that we can observe 36 possible outcome, and during in that process we are getting a sample space which is having 36 element, and each element we can call it a sample point. Sample point, you can give it name. Now we are taking another time. So this is situation of uh, discrete situation. It is because here point we are calling 1 2 3 point 3 4 5. So that means there is a bijection with set of natural number. So that's why this is a discrete phenomena, and when we are unable to see bijection of sample space with what we call it set of natural number, that time it will lead towards what continuous phenomena. Such situation is coming in waiting time. Consider the random experiment of waiting for a bus that will arrive at a random time in the future. Suppose you are just waiting for some bus at a particular bus stop, then that time it always moves in a continuum fashion. So if you try to observe, then that would be a continuum, continuous phenomena. It would be continuous value, that sample space, the outcome would come in a continuum fashion. Suppose if you are waiting at a particular bus stop, then one bus may come just 0.001 second, just after 0.001 second, and some another bus may come even after 15 minutes or something like that. So we don't know when bus will come, because just assume that there are enough amount of buses. So definitely you will observe that waiting time happens in continuum fashion. So in that perspective, what would be sample space? So sample space would be simply you may go to zero time. Zero time, it is your initial time. Starting from zero time, it may go on. So infinity is not a number. It simply say that it is very big, something very big, we are unable to reach there. So that is the meaning of infinity. Infinity is, it is a symbol, it is not a number. If you try to understand infinity, infinity, it is just a symbol. It says that it is something big that we can't reach. That is meaning of that. So sample space is coming that perspective in case of waiting time example, where bus may come anytime like this way. So in that process, sample space would be this. uh, Here closeness at 0, openness at infinity, because infinity is not a number. So this is the sample space for this experiment, second experiment. You can say that it is example number 1. This one is example number 2. Any question till now? If you are having any question, you can ask. Otherwise, I will go forward. Now, third example, I am taking it flight of bumblebee, or simply you can say that bee. If you try to see the flight of bumblebee, definitely it is random in nature. You can't predict where it will go at just here. One thing is mentioned, that here flight is function of time. It is function of time, because with respect to time, that bumblebee or bee is flying in a random fashion. So we can't predict where in next time. If we are seeing a bee at present moment at somewhere at some point, at the next time we don't know where it will go. So very random in nature, highly unpredictable. But don't worry, probability is giving a tool to approximate that prediction. Approximation we will learn in later modules. So a bee is buzzing around and we track its flight trajectory for 5 seconds. What possible outcomes are there in such a random experiment? What are the all possible? What would be sample space? So what would be sample space for this random experiment? Here random experiment is that, and that flight of bee, bumblebee or bee. So if you try to visualize the flight path of the bumblebee, geometrically it would look like this way, zigzag, very highly zigzag. So if you try to position, map position with respect to time, then very zigzag kind of graph you will get it. So sometime bumblebee is here, next time it may be here, next time like this way. So very zigzag kind of thing situation you are getting it here. So this is one flight, one path of the bumblebee. Okay, so if I'm asking one path, it is, that means one possible outcome. It is one possible outcome it is given here. So likewise, if you consider this, definitely it is a random experiment, that flight of a bumblebee. Then if you try to find out what would be sample space, then sample space in order to the, as we have not yet discovered the secret of teleportation, their flight path cannot have any jump. There would be no jump, there would be continuity. You know that if you try to observe b, it would be a continuous path, continuous function. It would be continuous position, would be a continuous function of time. So the sample space for this experiment would be here. You can say that I might be little bit specific in sense that we are putting a continuum approach, that position happens to be a continuous function of time. Just avoid few problem. So sample space, simply it would be collection of all continuous function defined over the this time period, 0 to 5 second, 0 second to 5 second. So this sample space is all continuous path. Simply when someone is saying that the path, continuous path, it always happens to be a function from interval, closed and bounded interval to a space or wherever where you want to position. Where if you want 2D position, it would be R2. If you want 3D position, if you observe 3D movement of this bumblebee then your codomain would be R3. If you would like to go for four dimensional, it would be R4. Depends upon your choice where you want to observe the flight of bumblebee. So if you try to make it planar, then R2, and if you try to make it a space wise, then it would be R3. So here sample space of this experiment would be what? Collection of all continuous function which is defined over this time interval 0 to 5 seconds. Okay, so this is the sample space. Okay, here this sample space omega, it faithfully describes all possible outcome of this random experiment. You can observe that we observe here, it is already mentioned that we observe the trajectory of the flight of bumblebee only for 5 seconds. So that's way this one is already fixed here. It is already fixed here. Okay, so it is the sample space of this random experiment. Going further, I will talk about event. I told that just for understanding purpose, event it is talking about some possible outcome. The meaning of just a minor difference between all and some. So see the difference between all and some. If you are from linguistic, then you can also see that difference. So here, once we have defined all possible outcome of a random experiment, we should discuss what types of question we can ask about such outcomes. So that means we are being more specific. Once we have already seen a random experiment, we are trying to be more specific in that process. That means we are going towards a specific or particular event kind of approach. So such outcome. Okay, this lead us to the notion of event. Informally, an event is a statement for which we can determine whether it is true or false after the experiment has been performed. Okay, so suppose example, if you are taking it, I haven't written it, so just I told that event is some possible outcome. So in layman way, in short way, you can say that. So same example, I have taken it, two dice. Consider the random experiment of throwing one red die and one blue die. Okay, we denote one sample point ij as an order pair, where I is coming outcome from the red die and j is the outcome in the face of blue die. Okay, that come out. Now here we are defining event like this way. Consider the following event. The sum of numbers on the dice is 7. Sum of the number. So that's where it is talking about some possible outcome. It is not talking about all possible outcome. See the this statement. Event is always a very valid. It is a valid statement. See, it is event is what is event? It is talking about the sum of numbers on the dice is 7. These events occur in a given experiment if and only if the outcome of the experiment happens to lie in the following subset. What would be subset? Just before going to that subset, I would like to ask, what would be that this event? Tell me, what are the elements of this event? Anyone may respond. Yeah, very nice. I know everyone might be aware of that, but just I want to see what is your approach. So approach would be definitely it would start from we know that sum is 7, so we will start with 3, 4. Then it will go on. Okay, I have to set this mouse. It is very sensitive right now. So here I have already written it. So it is already written. We are starting with 1 6 2 5 3 5 3 4 4 3 5 2 6 1. There is a pattern, so we should follow pattern in order to make things more systematic. So this pattern looks fine. Okay, so this is the event of event that numerically if you try to write in the form of sample points, this is the event. Okay, definitely event is always a subset of the sample space. It is always a subset of the sample space. It is okay. This is the event. So likewise you can take various example. Another example here, what we can say that we cannot predict in advance whether this event will occur, but we can determine whether it has occurred once the outcome of the experiment is known. If outcome of the experiment is known, we can determine whether it has happened or not. Some outcome, if we observe some outcome from the experiment, that means we perform the experiment. We have already observed some trial of the experiment. Based on that, we will try to determine the probability of particular event. Okay, if that particular event contain the outcome that is already we have seen, then definitely it will talk about occurrence of the particular event. So here I am taking another example, waiting time. Here we will define few event. So waiting time, it is talking about consider the random experiment of waiting for a bus that will arrive at a random time in the future. So sample space definitely it would be 0 to infinity. Now here what is the event? Event is talking about the bus comes within first hour. So within first hour, what does it mean? It is talking about interval. So event would be interval 0 to 1. This is the first hour. This is the event. Just this highlighted part is what it is event, and it is already written here. This is the event in this example. Likewise, someone is waiting for someone will say that what are the other possible event. So here there are infinite event. Because why? Because sample space is infinite. But in first case, what was the definitely if set is finite, then what are the possible event? Tell me if how you can find all possible event in a finite sample space. Any idea? What actually I could not listen you. What you mentioned? Actually, actually can't say much about that. Your perception. It is very simple. Actually, you may try to think it from set perspective. What is happening? It is talking about event is what? It is just see it here. It is talking about subset of sample space. So, in order to calculate all possible outcome, what is meaning of all possible outcome? It simply says that try to find all possible subset of the given sample space. So if you are having a set with n number of element, what are the possible subset? What would be all possible subset? In set theory in high school you might have already seen that now. That one is 2 to the power n. So that is that. Yeah. So that's why here n is what? It is talking about finite number. So that's why if you come to know your sample space is finite, if sample space is finite, then you can talk about all possible outcome. That sample space is finite, it is, that means cardinality of that sample space is equal to n, some fixed natural number. Then you can say that this one is having 2 to the power n number of events, possible event. Yeah. If your sample space is infinite, you can't say how many would be there, even your sample space itself. So for real number, generally quantity we use to introduce by c, uncountable. This one is uncountable number c. So there it would be 2 to the power c. Then c itself we unable to count. Then how can we say that about 2 to the power c? That one. So there is no such situation that we can count number of events in case of sample space when it is infinite. Okay, but in case of finite we can count. So that is the scenario. So this is the possible outcome, we can say that. So these are part of what we call it combinatory. Like in permutation combination, in high school you might have already gone through permutation combination. So from there you can derive such things. And really I would like to see all of you just recall those permutation combination in order to understand calculation of probability in a better way. Okay, so I'm going further. I will talk about probability measure and that probabilistic modeling, how we can measure probability. And just we have to summarize everything by saying that we are doing a probabilistic modeling, and how in probabilistic modeling what we do, how we approach things. So just probabilistic modeling is, it is a very systematic word in order to accumulate all things what we have already covered till now. So coming to probability measure. So after specifying the sample space, we have till now we have done sample space. We know about sample space. We know about event. In a random experiment, we know sample space. That means all possible outcome. We know event. That means some possible outcome. We know these things. Okay. After that, we try to reason out something about probability measure. So now we see how does a random experiment work. So what you do? You pick one outcome from this set of all possible outcomes that we are calling it sample space omega. Once this outcome is revealed to us, we can check for an event A whether or not that event occurred in this realization of the experiment by checking the that outcome what we have already you have picked, whether that outcome is in that event A or not. If the outcome omega, small omega, is in the event A, then we will say that the event A occurred. If it is not in the event A, then simply we say that we don't know about whether A is occurred or not. It may not occur. So that situation will come. So this is the checking, investigating way to occurrence of to find that whether event A is occurred or not. So all these are very complex things. So unfortunately, we have no way of predicting which outcome you will pick before conducting the experiment. So if you suppose someone is conducting a random experiment, we can't say that one person will come and what will pick. We can't say. We can't predict in prior. So we can't predict, but we can measure using some proper approach. So we therefore also do not know in advance whether or not some event A will occur. We don't know in advance. In prior, we don't know all those things. So in order to quantify all this, to model a random experiment, we will specify for each event A our degree of confidence about whether this event will occur by assigning a number that we are calling it P of A, that means probability of event A, and we are putting a condition over this assignment number that this number would be always between 0 and 1, including 0 and 1. Always it would be 0 and 1. So we are just introducing probability measure, which must obey some rules that encode our common sense about how random experiment works. So probability is something more than common sense. Simply we are having a common sense, then we are assigning assignment number, and then that number we are and that assignment number is satisfying certain number of assumption or properties, and then we are calling that assignment number P of A is a probability to the event A. P of A probability. Suppose if probability that assignment number P of A is equal to 1, then we can say with certainty that that event will occur. That means it is very deterministic situation. In this case, A will happen every time we perform the experiment. So in an experiment, we observe that if a random experiment we perform a random experiment, there one event is associated whose degree of confidence is equal to 1, then we can say that that event always occurs. One example is sample space. If you perform a random experiment, if someone is asking what is the probability of getting sample space, then definitely it would be always 1, because sample space is talking about collection of all possible outcome. If you perform a experiment, random experiment, definitely it will say that performance of that experiment, it will guarantee that at least one event outcome will come, and if at least one outcome will come, that the occurrence of that one outcome is talking about occurrence of sample space. So that's why probability of a sample space is equal to 1. If you take a subset of sample space and something so if you try to perform a random experiment and that outcome is not from the subset, then simply you will say that that subset is not occurring. So probability would be less than 1. So probability will decrease from 1 to, if you reduce your subset from sample space to a smaller collection of outcome, then definitely probability it will keep on decreasing, and finally it will decrease up to what? 0. If you nothing is, if you you are not you don't have any outcome, then what will be probability of that? It would be 0. So that situation is coming if you are having an event, suppose a null kind of event, null set kind of event, and if then definitely it will have probability 0. What does it mean? We are also know that if probability of that event is 0, that means it is, we are very much certain that A will not occur. If probability equal to 0, it is talking about non-occurrence of the event A. So A will never happen in any of experiment, like uh, anything, and impossible thing. Just take impossible kind of thing. Suppose someone is saying that one person will come and try to hit every ball to out of the boundary. So definitely that there is no such kind of player, there is no such kind of person that who can hit every ball out of the boundary. So that that event is totally null. So that situation, in practical situation it is not possible. So that situation you can say that. Now suppose if you are taking an event with probability is 0.7, so that means, yeah, say that the event will occur in some realization of the experiment, not in others. That means in some portion that event will occur. If you take outcome is coming from other out of that realization, then simply we will say that outcome that event will not occur. That means simply we say that we are 70% confident that that event will occur, and 30% we can't say it. We don't know, it may not occur. So that's way that when number is coming between 0 to 1, it's talking about realization concept. That means some kind of condition we are putting it. Going further, I will talk about probability law. That means I discuss about probability measure, that assignment number P of A. Now when it become law, when that assignment number will satisfy certain number of axioms, certain number of assumptions, then it become a law. Intuitively, this specifies the likelihood of an outcome or any set of possible outcome, or simply in simple way you can say that event, or simply you can say that some possible likelihood of some possible outcome. So a probability measure is an assignment of the number p of a to every event a such that it satisfies the following axioms or following assumptions. First, that assignment number is always lies between 0 to 1, and that we are calling it degree of confidence. Also you can layman way you can say that it is always a non-negative number, non-negativity you can say that. Second assumption, it is talking about normalization. That means if you take all collection of all possible outcomes, that means sample space, then definitely in that the happening of that, if you perform an experiment, then always it will say that it will talk about occurrence of the sample space, because every outcome is falling in that sample space. Definitely probability of sample space would be always 1. It is talking about normalization condition. Okay. Now, third condition, it is talking about mutually exclusive. So, second is talking about exhaustiveness or normalization condition. So, if you are coming from set theory approach, that normalization condition you are means it is talking about occurrence of sample space. That means all possible. We know about all possible event associated with that sample space. That means exhaustive nature. We know exhaustive nature. So, in set theory purpose, that normalization you can translate it into exhaustiveness. Okay. Now, third property is talking about mutually exclusiveness. So, these two are very important words. You need to understand that. I would like to say that try to understand this. So, if A and B are two events and there is no common between A and B, that means A intersection B is 5, null set. Then we can easily calculate total probability of A and B. That means probability of A union B, it would be just probability of sum of the corresponding probability. The probability of A union B equal to probability of A plus probability of B. That means it is talking about mutually exclusive events. They add up their probability in order to get total probability. So all these are basic. You don't need to prove things. Universally, you have to accept these are true. These three are true, and just based on this, if you try to conclude anything, always rely on these three. Always come back to these three and use as much as possible. So all about mathematics, how much you know about how much idea you are having to apply the previous concept. So if you are able to try to draw any conclusion from the problem, just use these things maximum, in maximum way, definitely your problem will be solved. So these three are very essential. Okay. And this apart from defining that assignment number, that assignment number is have to satisfy these three properties. Now, so now question would be here, you all can ask one question, how we can calculate that assignment number P of A. Very simple question would come, how we can calculate. Then you can calculate it through various approach. One approach that we told that hierarchical definition, it is saying that probability of a we calculate it through ratio. That means we are talking about probability of a equal to number of times that a is occurs, number of times that a occurs. Simply in short I will write hash is talking about number of times that a occurs. Okay. Hash is talking about count. This notation might be clear to everyone, divide by number of times all possible collection of all possible outcome. So that's why I'm putting it as of omega. So this definition, this we are calling it hierarchical definition. This definition becomes a interesting definition when it satisfies all these three properties. Apart from this, so it is one way to calculate this assignment number p of one way. So it is only feasible in case of what we call it when our sample space is very small. In that case, these things are working fine. So these things are feasible to calculate when but later we will go to calculate in different approach. So I will talk about those things. So one simplest approach is like this way. Okay, and this is the probability law. So further we can generalize this third assumption by saying that we are taking a collection of event which are mutually exclusive, pairwise mutually exclusive. Here this one is talking about you are taking a collection of event which are pairwise mutually exclusive. Then we can calculate the probability of union of all those events. How? Just by summing the respective probability. Just sum the respective probability of the event, you will get so it is talking about again a generalization of mutually exclusive phenomena. So it is all about just generalization from three. So only these three law you need to understand, you need to visualize, you need to, as much as if you have any problem let me know, and just try to understand. These three are very important. Now one question you can, I told that one question you can ask me that how we can calculate this p of a. So that one is different question. You can come up some technique to calculate p of a, that probability of a. But why? Because that one is a number. We need to know some numerical approach to calculate p of a. So that things you will automatically you will learn in later lectures. Okay, and but that assignment number, it becomes a probability measure when that satisfy these three properties. Then it becomes a probability measure. If there is some kind of failure, then simply you can say that no, it would be not a probability measure. Okay, coming to a few more remark for the probabilistic model. Intuitively, what probability, if you try to go for intuitive approach, probability study and compute, and you can say that quantify randomness of an event. If we flip a coin many times, then the coin will come up heads roughly half the time. If you, this one is talking about law of large number. You roughly many times you are flipping a coin, definitely roughly we with roughly we can say that with based on some law that or some that I told law of large number, 50% chance is there head will come and 50% chance is there tail will come. So that is based on law of large number. Thus we say that probability that the coin will come up head is one half, that means 0.5. More generally, our common sense intuition about probability is in the form of frequency. So that ratio thing what I told. So if you repeated a random experiment many times, the probability of an event is the fraction of these experiment in which the event A occurs. I told that when you tossing coin, you suppose you are tossing coin 10 times, and in 10 times 3 times you are getting head. So simply from that perspective, this ratio approach, you can say that probability of head would be 3 by 10, but that one is not true. 3. So in long run you will see that 3 by 10 or then 5 by 10 or something like that. Finally it will converge to, the probability will converge to 0.5, 1 by 2. As we have seen, the heuristic definition in terms of fraction can lead to ambiguous conclusion. This is why we do not define probability as frequency. If you define probability in terms of frequency, it must have to satisfy those three laws. Okay, so instead we make an unambiguous mathematical definition of probability as an assignment number P of A that agree with all those three assumptions. What I told, that A, B, C, again I have written. So this one is talking about probability must, that assignment number. I'm not saying probability. I'm saying that assignment number or probability measure, it must between 0 and 1. And the if you take all possible outcome, then the probability it will sum up to 1. Second probability we are talking about normalization, and third probability it is talking normalization, also you can say that mutually exclusiveness. So everyone remember that second probability, another name you can say that mutually exclusiveness, sorry, exhaustiveness. Second probability is talking about exhaustiveness. Remember, try to remember exhaustiveness. So it is talking about exhaustiveness property. And third one is okay, mutually exclusive exhaustive. Okay, this mouse is little bit sensitive. I will just try to change the setting. And third property is talking about mutually exclusiveness. Okay, mutually exclusiveness it is talking about. So these three are main property of probability measure, being a probability measure. So at last, if you bring all those things together, then we what is meaning of that? We are doing a probabilistic modeling. Say, so we can say that a probabilistic model is a mathematical description of an uncertain situation in accordance with three ingredients. First one is sample space, second one is probability law, third one is probability measure. So all these three. So if you are taking account all these three in together, then that means you are doing a probabilistic model. Geometrically, you can see that like this way. So you perform an experiment. This is the experiment. You perform an experiment, then you are noting down all possible outcome, that we are calling it sample space. In that, within the sample space, we try to choose some outcome, that some outcome, one is falling event A, another falling event B. Then we with respect to each outcome, each event, we try to assign some number. So with respect to the event A, we have assigned this number P of A. With respect to event B, we have assigned this number P of B. So all these, when we are doing all these things, that means we are doing a probabilistic modeling. So it is all about today's lecture. Regarding attendance, just mark your roll number there in